Morning, ladies and gentlemen. Welcome to a short week. Lecture 31, November 7, November 8 is a big day in this country. As someone who grew up in a different country but is now a citizen here, I would like to point out that this election has been a lesson in civics. Right? It has been, you have seen day after day after day the effect that another government agency can have on an election campaign. The effect of the press, right? That the press are free, biased, unbiased. The effect of the press is enormous. And I think we've also come to realize that elections are not about us finding someone we like. It's not a matchmaking service. What we're trying to do is appoint the government of the United States. That's the job. From among the available people. The available people were arrived at by a democratic process. And that process may be flawed, but it's a lot better than a lot of other processes that are out there. And so I hope that you recognize that you have an extraordinary opportunity to really determine your own futures. What governments do matters much more to you than it does to me. I'm just older, right? It's just going to have less effect on me because I'm going to be gone a lot earlier than you. So it is actually really important that you take your part in appointing the government of the United States. So whatever it is, don't be looking for somebody who makes your heart go pitter-patter. Just look at what's out there, and you have to make a choice. It's a responsibility. I have never made a political speech in a class before, but there is a group called TeachNet. It's an email listserv of faculty on campus who are particularly interested in teaching. And there's been a lot of discussion of what will we say on Wednesday. On Wednesday, I'm not going to say anything. On Wednesday, we're going to talk about bootstrap for regression. That's because Wednesday it's done. Monday is the important day. And so this morning, somebody sent something saying, forget Wednesday. Just remind our students of their opportunity and their responsibility. So I have done my part, and I hope you will do yours tomorrow. I heard, by the way, there's a woman running for president. And, as somebody who grew up in India with Indira Gandhi as prime minister, I just don't know what the big deal is. Right? That was way back when, and it was India. And Sri Lanka down had Mrs. Bandaranaike, and, Israel had, I don't know what the big deal is, but apparently it's a big deal. Okay, but I've heard that women who go out and vote, take their I voted stickers and put it on the gravestone of Susan B. Anthony. We don't have that opportunity. It's a bit far. But symbolically, maybe we can do something like that. All right. I have to say, though, I watched President Obama being interviewed by Bill Maher on Friday. And I was sitting there going, could we change the Constitution so that this guy can be around for another 4 years? I don't know. It's just, if you just compare what's out there, you go, we had it pretty good, actually. Sorry. Make your own decisions. This is my personal opinion, which is now, by the way, on course capture. It is on record for posterity, and probably somebody's going to have to cancel this video because of that. I don't care. This is actually a hugely difficult thing for faculty. We talk to our students, and sometimes we talk to them not as faculty teaching the course materials, but just as faculty. And then that gets captured for posterity. And then somebody starts worrying about lawsuits. And I just threw up my hands at one stage and said, you know what? I'm just going to talk to my students. And if I've said something offensive, I will apologize. But that I will not talk to my students because somebody is capturing me on video, it just seems to tie my hands. We have a very different relationship if I'm always worried that somebody's going to sue me. So I'm trying. All right, can we get to work? Let's get to work. As always, this thing doesn't budge. Okay, there we go. Okay, so there's a project deadline, and I hope when you get to the end of the project, you will see a graph that actually a bit of an aha moment. homework as usual, short week. We have an academic and administrative holiday, so no lecture and no office hours, though Wednesday and Thursday will be as usual. All right. So we were talking about estimation on the past couple of days, and we've been looking at scatter diagrams, and we have figured out how to put a straight line through a scatter diagram following Galton, who saw the straight line somehow for football-shaped scatter diagrams. And then we went one step better and said it's the exact same straight line, regardless of the shape of the scatter diagram, if you are using minimizing mean squared error as your criterion. So the straight line whose equation we developed is the least squares line, no matter what the shape of the scatter diagram. And today's lecture is going to be about the errors that we make. After all, an estimate isn't worth anything until you can quantify how far off you might be. And so we have the least squares line that we just talked about. There's a number of names for it. And so now what I want you to do is imagine a scatter diagram in your head, any pair of variables, and you have decided that you're going to fit a line through it. We know how to do that. It's called the regression line. So you fit a line through it, and now the question is, was that any good? Right? How does that do as an estimator? The errors are called residuals. So errors from what? The actual point minus the corresponding estimate from on the regression line. These are called residuals, so every point corresponds to an error. I think you saw some of these errors in Friday's lectures. And so what is a residual? It is the observed value, that is the height of the actual point, minus your estimate, that is the height of the line, at that value at the corresponding value of x. So it is a vertical difference between the point and the line. Please note that I'm using the word difference, not distance. This carries a sign. A residual is positive if your point is above the line, and a residual is negative if the point is below the line. So residue in English is what's left over after some process. So we're somehow imagining that when you estimate, you've picked up what you're trying to get, but then there's something left over to get to the observed value, and that's called the residual, hence the name. And so what I would like to do is calculate this thing, and today we're going to look at how to use it to see whether we've got a decent regression. So some stuff that is run every single time, and then, okay, take a look. Our collection of functions is growing. We've got standard units, which then lead to correlation, from which you can calculate a slope, based on which you can calculate an intercept, based on all of which you can calculate the fitted values. And those that is a set we've been developing over the past few days. And now we have residual. Takes the same arguments, the name of the table, the column label for x, and the column label for y, and it returns the observed values as an array minus the fitted values. Those are exactly the residuals. And so here are the data set that has been a running example for now several days. Mid-parent height used as a predictor for the response. The y variable is called the response. So the mid-parent height is the predictor for the response, which is the child's height. We have the fitted values. If you draw a graph of the fitted values, what will the shape of that graph be? This should be sung out. If you draw a graph, your x on the mid-parent heights on the horizontal axis and just the fitted values on the vertical, what shape of graph will you get? You'll get a straight line. The fitted values are all on the line. It's the actual observed points that are all over the place, right? And so now you have the residuals, and this number is simply the difference between the actual child's height minus the fitted value. Okay. And so the best thing to do to try to visualize is, to understand something is to try to visualize. This is a diagram that you've seen before. That is the scatter diagram with a line through it. What we're going to do now is we're going to draw something called a residual plot. Corresponding to each of these points, there is an error. So corresponding to that point, the error is the difference between that height and this one. Corresponding to this point, the error is the difference between this height and this one. That's a negative error, quite large. So what we're going to do is we are going to plot the predictor variable mid-parent height on the horizontal axis, but on the vertical, we will plot not the observed values of the child's height, but the errors. We're just going to examine the errors. And that's called a residual plot. I am not so interested in your ability to do fancy graphics. So actually, let me just to tell you what you are responsible for understanding and what you may understand if you wish or not. Take a look at scatter fit. Okay, you are responsible for understanding what that first line means. Def, name of function, arguments. Yep. Okay, this is a table method. I expect you to understand much of it. So table.scatter, you have used this forever. This is the variable on the horizontal axis. This is the variable on the vertical. Yep. This s equals 15 gives you the size of the points. I don't care if you know what that does. Then subsequently, you see that everything starts with plots. We are using matplotlib, a Python mathematical plotting library. We haven't taught it to you. We use it because it puts labels nicely and so on. If you don't understand what that does precisely, it doesn't matter. You can ignore any line that starts with plots. It's just there so that we have the right labels and so on. All right, so I'll do residual plot and regression diagnostics. Diagnostics, I'll say what that means in a minute. What we have is the original plot and the residual plot. A diagnostic is when you are trying to go through and figure out, whether how well something is doing and how what is going to be the quality of any future prediction. Yes. The fitted line is the regression line. Yeah, line of best fit, least squares line, regression line, fitted line, exactly the same thing. So this is the regression line, and now take a look at what's happened here. You've basically twirled this one so that it's become horizontal, and you're just looking at the errors. Take a look at that. That is a blob. And the fact that it is a blob tells you something about your regression. You can see, for example, by the way, take a look at this flat line at 0. If I look at that, the errors are about half above the line and about half below, yeah? So errors kind of averaging out to 0. That's what it looks like. That's not a surprise. We'll actually look at that in more detail. But every residual plot that you draw will be on either side of 0, some plus, some minus, and it will turn out that every residual plot will overall be flat. You can't see a trend in a residual plot because whatever trend there was has already been used up in your line. Okay, so you have necessarily a flat plot that is no overall upwards or downward trend. This one is a good one because the positive errors look kind of like the negative errors, and it's about equally spread out throughout in the bulk of the data, right? At the edges, it's hard to tell because you have very few points. So what this is saying is that when you fit your straight line, your estimates were about equally good throughout. It's not that they're better in some places and worse in other places. It's not that they're in general low in some places and in general high in other places. That blob there should be in your mind as the residual plot of a good regression. Okay, looks like a blob, symmetrically above and below the horizontal line at 0, similar vertical spread, and no pattern. Right? So now, of course, the question is, well, what does it look like when it's a bad regression. And so for that, one of the problems that you can have with the regression, as you've seen before, is that the scatter diagram was nonlinear, but you went ahead and fit a straight line. Right? That may not be the best thing to do. So nonlinearity can be a problem, your original scatter plot being curved. So how do you find that? Well, okay, so I had to show you this guy. This is a dugong, and there's a lovely data set about the, we have to protect these guys. They're relatives of manatees, and these particular ones were near Australia somewhere. So, you know, if you're going to protect a population, you have to kind of know its demographics. So how old these creatures are is important to know. And, well, you know, they don't have birth certificates, and they're not likely to come and tell you how old they are. And so there's data on how do you figure out how old they are? Well, you can't go up and talk to them. You basically look at deceased dugongs. And a standard method is to look at the teeth, right? The sedimentation on the teeth and whether it's being honed down and so on. These are used for many animals. And so there is a data set on that Statistical Science, it is one of the journals, has on the length and the age of dugongs. Length is in meters and the age is in years. So there's a young dugong, 1 year old, and there is a senior citizen, 31.5 years old. And the point I am making here is that these ages are estimates. Now, these are estimates. Typically, the estimates are made based on teeth, but length is actually something that you can measure from a ship, from a dugong that is swimming around, if you are good at measuring length. So it would be interesting to see, if I know the length of the dugong, can I say something about its age? So if you try to answer that question, you can run a regression of age as your response variable, on length as your predictor, and what we will do is we will see whether that seems, well, correlation is pretty high. 0.83, and so here are the two plots. There are your data. Length on the horizontal, age on the vertical. You can see a curve, yeah? A curve is a lot more visible on the residual plot. It's just because the scale is bigger on the residual plot. So residual plots are often used to identify nonlinearity. And how are you seeing nonlinearity on this plot? You are seeing that the points were in general above the line at the low end of your predictors. Then they were in general below the line. And then they were above the line again. Right? So if you have a straight line, the points are above, then below, and then above. That's your curve right there. So the residual plot shows up patterns more clearly than the original plots, and that's why the residual plot is used to identify a pattern. There is still no overall trend. There's never going to be. But patterns are visible. And so when you do a regression, step one, before you do anything, draw the scatter diagram of the original data, calculate a correlation, run your regression if you feel you ought to, but then please also look at a residual plot, because if you have some problems with your regression, that is more likely to throw it up. So this is one problem. Actually, let me stop for a second. Any questions about this thus far? Okay. There's another one, which has a wonderful name. Heteroskedasticity. Hetero, different. Skedastic, spread. Variable spread in the scatter diagram. You can see that in a residual plot as well. So let's go back to a data set on cars. You've seen these data before. This is all hybrid cars that were built up to about 2013. And what I'm doing is I'm looking at the relation between acceleration and mileage. And we've seen before that that's a negative association. And so, you plot a straight line, doesn't look so terrible. It's not clear whether you're seeing a curve or what you are seeing. It's certainly not that beautiful football that we have seen in, say, Galton's data. The residual plot shows you something interesting. What the residual plot shows you is that it's V-shaped. It's flared. The errors are, in general, much larger at the low ends of the acceleration than at the high ends. So what this is saying for your prediction is that you can make your regression prediction throughout, and, it actually, graph doesn't look that far from linear, but the predictions aren't equally accurate for different values of acceleration. They may be a little more accurate for higher values of acceleration than they are for lower values. And so if you are trying to use such a regression to make predictions about the future, then you can't just make the prediction, but you have to look at the prediction going, okay, so what kind of value was I given? Is this going to be typically a more accurate prediction or a less accurate prediction? You can pick up flare from the residual plot. Okay. So these are visual diagnostics, and the two most important ones are nonlinearity and uneven spread that are visible on a residual plot. And so please don't do any regression without A, having plotted the original data, and B, doing the residual plot. And that's why we've given you a function that does both at once. Okay. So these are visual, but we ought to be able to quantify some of what we have seen. And the first thing that I am going to do is tell you something that at this stage I can't prove in a class like this. But no matter what the shape of the original scatter, the residual plot is overall going to be flat. And a way of saying that is, so on a residual plot, what are the two variables? On the horizontal axis, you have the predictor. On the vertical, you have the residual. If I'm saying that that plot is flat, what I'm saying numerically is that the correlation between those two variables is 0. If you look at the correlation between the residuals and x, that's 0. Why is that? What's the residual? It's what's left over after you have used the linear regression, the line, to make your prediction. Yes? So any linear association between x and your variable should have been picked up by your best line. So what's left over is all somehow the nonlinear stuff. So there is no linear association left between your residuals and your x. And what I'm going to do, so the reason for telling you this is if you draw a residual plot and it looks like it's going up, you have done something wrong. It's not that the regression was bad, you've done something wrong. It's not possible. Right? If you've drawn a residual plot and it's overall looks like it's going down, then also you have done something wrong. Every single residual plot, good regression, bad regression, is going to be overall flat. And just to check that, okay, so here I am, let me just, before this, diagnostics. Just draw you the scatter diagrams name error. Diagnostic plots. John wrote this function last time. Okay. I should know what my functions are called. Okay, here we go. So there's a residual plot. What we're saying is that the correlation between these residuals and this midparent height is 0. That is not at all surprising looking at that plot. And we will run our function correlation, takes the name of the table, the names of the two columns, and okay, so what is that? That looks like a mess, but it is a very, very small number. Yes, you see 10 to the power minus 16 there. And so what that is, mathematically, if you just do algebra, and this is the beauty of mathematics, it comes out to be equal to 0, and you can put a period there. But this is actually doing a computation, and there's rounding error. And so what I'm doing in the future is I'm just going to round these things to 10 decimal places. Okay? And if I round to 10 decimal places, okay, notice the minus 0.0. I love that. That is because by rounding error, it came out to be just a tad below 0. Okay? Correlation 0, same thing with our dugongs. If you run the regression and then do the correlation between the lengths and the residuals, 0.0, the residual plot is going to be flat. Regardless, so one regression was good, one regression was bad. Both of them, the residual plot is overall flat. Okay. There's something else that we talked about last time that it will be no surprise to you. If you average out the residuals, what do you think you're going to get? 0. The plus residuals are going to exactly cancel out the minus residuals, just like the plus deviations canceled out the minus deviations. Whether the regression is good or bad, the residuals are going to average out to 0. So np.mean heights.column residual. And again, I'm rounding. What do I get? I get 0. Okay, great. How about our dugongs? A bad linear regression. So you take dugong.column residuals, takes the mean of that, 0. Okay, so the residuals will average out to 0 regardless. And so where are we here? Again, if you run a regression and you average out your residuals and you get something that's not 0, you have done something wrong. So it is nice that our errors, on average, we don't make an error, but then you would like to say, okay, so on average, yeah, but for every single point you do make an error. So how far off are you from average? So you want to get some sense of how big the errors are. And here, again, we'll do, I'm just going to tell you something. And what I think you are realizing, we're coming to the last month of this course, and I am hitting the limits of what I can explain intuitively in formulas that I can develop by intuitive calculations. We are now getting to specifics, which actually require mathematics, but even something like this, it is possible to understand what it is doing by just looking at the bits. So first, this is the SD of the errors. Right? And what you're noticing, and we'll look at this some more, is that it's the SD of y, it's the SD of your children's heights, if you like, times something. And what we're going to do is we're going to look at that something. R is a fraction, you agree? It may be negative, but anyway, whatever it is, it's a fraction. R, the correlation. Yes? What about R squared? It's also a fraction. You take a number between 0 and 1, you square it, you get another number between 0 and 1. What about 1 minus R squared? So 1 minus a fraction is a fraction. Yep, still a fraction. Take the square root of that. What do you have? Another fraction. Yes, so that whole mess, root 1 minus R squared, is some fraction. Okay. And just to keep us an idea of what's happening in your head, if R is equal to 0.6, R squared is 0.36. 1 minus R squared is 0.64. Yep. Square root of that is 0.8. So I started with a fraction R that was 0.6. I did root 1 minus R squared. I got a different fraction that's 0.8. Regardless, it's a fraction. So what we have noticed is that the SD of the residuals is a fraction of the SD of y. Now, why fraction and so on, we will examine in just a moment, but I just want you to look at this and just recognize that it's a fraction. So the first thing we're going to do is check in our particular instances that this is actually a correct result, and then we're going to look to see how we can use this to see whether our regression is any good or not. So if I go to so if I run that cell, that just says no matter what the shape of the scatter diagram, the SD of the residuals is the formula that we just had on our big slide. Okay, so what we're going to do is, for our heights regression, we are going to calculate both sides and check that they're equal. The left-hand side is the SD of the residuals. Therefore, np.std of something. Of what? My table heights had a column called residual. So I will calculate the SD of that. And it comes out to be about 3.4 inches. It's in inches because I'm measuring heights. Okay, so now what I need for this is I need to find R. I need to find the correlation between the predictor variable, which was midparent, and the child. And then I need to do np.square root 1 minus r squared times the standard deviation of y. And I'm just not going to run that thing. I want you to look at those two lines and ask me any questions that you might have. What function is being used? What is going on? Yes?
Why did you use np.square root and not just to the power of 0.5?
Just because I felt like it. The question is, why did I use np.square root and not to the power 0.5? Also partly because having the word square root there, when you go back and look at it, it's just much easier to see what's going on. So I'm just using it for the language, really. So questions about why those two lines are being calculated. So that last line, when it is run, what will it give back to me? Will it give back to me an array, a table, a number, what? A number. And what we are hoping is, is that we know that it is this number, and we're hoping that it gives me the same as before. So I am now going to run this, and it's the same as before, apart from rounding. Yep? So in this particular instance, our result is true. What I'd like to do is I'd like to run an example where the correlation is negative. Our hybrid cars, acceleration, and MPG correlation was negative. And so what was it? It was minus 0.5, roughly. So if we play the same game and run the regression, then the standard deviation of the residuals is 9.4 miles per gallon. And root 1 minus r squared times the SD of y is the same number of miles per gallon. Right? So the formula, just by verification, is a good formula. And now I want to go back and take a look at what it is telling us. Before I do that, if you would please look at the code and ask me any questions about exactly what was calculated in the different lines. If you want to, take a look at a table or anything, just let me know. All right, so take a look at that. That says something about the SD of the residuals. It's important to keep in your mind, what's the average of the residuals? 0, right? So that number is saying the errors are 0 plus or minus something. That's what's being calculated there. So let's look hard at this. The extreme values of R are plus 1 and minus 1. You agree? So let's just take R equals plus 1. Imagine the scatter diagram in your head. What are you imagining? You are imagining a perfect straight line, I hope. Yep? So where is the regression line? It's the exact same thing as the scatter diagram if R is equal to 1. If the scatter diagram is linear, the best straight line is the scatter diagram. Yep? So how much error do you make in regression? 0. If the scatter diagram is exactly linear, the amount of error that linear regression makes is 0. Yep? So the average is 0, and there shouldn't be any variation. You're just not going to make an error. If you plop in R equals 1 in your formula, what do you get? You get 0. Okay? So this is a good answer for R equals 1. If you play the same game for R equals minus 1, in your head you are imagining the scatter diagram to look like what? A perfect straight line sloping downwards, which will still be exactly the same as the regression line. It will have a negative slope. Regardless, it will be exactly the same. How much error will you make? None. 0. Right? So the average will, of course, be 0 from what we've seen, but so will the SD borne out by the formula. Okay? So this captures the right thing at the two ends, and now we're going to look at the middle. Usually, root 1 minus r squared is actually some proper fraction, as we have seen. But now, the other interesting case is r equals 0. Okay? So think about r equals 0 and imagine your scatter diagram. R equals 0 says there's no what between the two variables. No correlation between the two variables. Okay, so in slightly more descriptive language, what could you say? What does that mean? No what? No what? No linear relationship between the two variables. That's what r equals 0 says. Yeah? So is it a good idea to use a straight line to estimate one variable based on the other? Doesn't seem like a good idea because there's no linear relationship between the two, right? So now we're going to see how that is reflected in this formula. All right, so supposing you went ahead and you said, you know what, this thing is overall flat, I'm going to fit a line anyway. If you fit a line anyway, your best line should what? Should it have a positive trend? If the graph is overall flat, your best line should be flat, okay? So let's just check that that happens. Anybody remember the slope of the regression line? R times something, remember? Yes, SD of y over SD of x. Regardless, R times something. Yeah, what's R? 0. What's the slope? 0. The slope of your regression line is 0. It's a flat line. Okay, so that's fine. That's fine. We're fitting a regression where there is no linear association. You know, nobody can stop us. We can do it. It's a flat line. So the question is, flat where? The flat line means no matter what x is, I am going to make the same prediction for y. You agree? That's what flat means. You vary x, I'll just give you the same answer back every time. Yeah? What answer should that be? You're trying to predict y. So you're trying to predict the children's heights, right? Or something, using something that's not related. What should you predict? The average. That's what you should predict. If I say, here's a student, I want you to predict their final exam score. I'm not going to tell you their midterm scores or their quiz scores or anything. What are you going to predict? You're going to say, well, I'm going to guess average. Yep. So I am actually deliberately talking this through because I want you to have some things in your head. So what we need now, we know the slope of the regression line is flat for this one. Yep. We need the intercept. Does anybody remember the intercept? Okay. So I'm trying to make you remember some stuff. Okay. So the intercept looks like this. It's the average of y minus a bunch of stuff, right? And the bunch of stuff has an r in it. Average of y minus r times something. What's r? 0. Yes? So r times whatever, forget what that is going to be what? 0. So when you take average of y and minus 0, what you're going to get? You're going to get the average of y. So your regression line is going to be flat. And it's going to be flat at the average of y, which is where it should be. Flat line. No matter what x is, you are going to estimate average of y. Okay, so now, in your head, you've got a bunch of values that you're trying to predict, and every time you come back and say, I'm guessing the average, you're going to be off every time. Yep? So you're going to be off by number minus its average. What's that called? Careful. You've got a list of numbers. Yes? You are predicting average. Your error is a value on the list minus the average. List minus average has a name. Deviation from average. Each of your errors is a deviation from average. What's the rough size of the deviations from average? There's a number that measures the rough size of the deviations from average. Which number is that? The standard deviation. And so what you have just discovered is that if r is equal to 0, the rough size of your errors is going to be the SD of y. You're going to guess average, and you're going to be off by the SD. And that's exactly what you get from this formula. If you plug in r equals 0, on the right-hand side, you have the SD of y. Okay. And so all I'm trying to do here is trying to give you a sense is for the values of R that are at the extremes, or for the values of R that have a very particular meaning, this is a good formula. Everywhere else, you have to believe that that's the right kind of that's the right fraction to use. Right now, it checks out, and it is indeed correct. It's provable at the level. I think Stat 88 is going to see a proof. But the main thing is that the error in regression is in general less than just saying average of y. It ought to be. Right? Because when you just say average of y, you're ignoring x. If you use x and there's a linear relation, you should do better. Right? So the fact that you're getting an answer that's less than the SD of y makes sense. And I will show you one other way in which this is commonly used. Okay, so let me run this thing. Take a look at this. SD of residuals divided by SD of y is root 1 minus r squared. True or false? What did we just say? SD of residuals was what? Root 1 minus r squared times the SD of y. Yes? Is that the same statement or a different statement? It's the same statement. Divide both sides by the SD of y. Yep? So the root 1 minus r squared is a ratio of SDs. It's SD of residuals divided by SD of y. There is a companion result which says that if you look at the SD of your predictions versus the SD of y, you get absolute R. And I'm just going to take a look at this, and we're going to do exactly the same thing that we just did and check that this thing makes sense. Take R equals plus 1. Yep. How do the fitted values compare to the actual values? R equals plus 1. Scatter diagram is a straight line. Where are the fitted values? On that line. Where are the observed values? On that line. What are the errors? None. Right? So the fitted values are exactly equal to the observed values. So if you take the ratio of those two SDs, what should you get? You should get 1. They're the same variable. Yep? The same is true if R is minus 1. If R is minus 1, the fitted values are exactly the same as the observed values. And so the two SDs are equal, and so the ratio is 1. Please note, the ratio is 1, not minus 1. It's a ratio of SDs. It's going to be positive. In general, it's R, and that, again, that's something that I'm not going to show, but it does answer a question that you asked me at the end of last lecture, which is supposing I have two predictors. Remember, with the shot put, we had a linear predictor and a quadratic predictor? Yep. How do I know which one's better? This is something you can do. You can calculate the SD of your predicted values relative to the SD of the overall values, the observed values, and take the one that's higher. Now, there is a minefield in that statement, but it's an easy first thing to do. Just look at your predicted values and your actual values. That's a natural comparison to make. Yes? Just compare the variability. Okay. So that has been a pretty long mathy discussion. It is to give you a sense that good regressions can be measured. One measure is high R. Right? The bigger the R is, the better your regression is. And you can quantify exactly what better means. So what we're going to leave you with today is one observation that we haven't made yet. Thus far, we haven't really done any predictions. I mean, all our data have been historical. If you take Galton's heights, and those people were living in the 1800s, we're not predicting their heights now. We had Little Women, the author is deceased. We just haven't made any predictions. And we haven't thought about sampling for a while. Right? We've just had a picture, and we've tried to say, what's the best line through it? So now here's a question. What if our picture, the scatter diagram that we have, comes from data that's a sample? Underlying that sample is a large population that we can't see. So we look at our scatter diagram, that's the sample, and we see a straight line. Does that actually reflect a linear relationship in a population? Maybe. If the sample is large and random, you kind of hope so, because the sample is supposed to look like the population. But you've seen a line through a sample scatter plot. Is it exactly the same line through the population? You're guessing not, based on what you know. The line through the population may be somewhat different. So how do I tie in what I'm seeing in my sample from what there is in the population? And that's going to be the business of the next lecture and 5 minutes. So I have 3 minutes here and another lecture on Wednesday. What I want to show you is something that's important to keep, that we just did that. That is Tyche, the goddess of chance. That's Tyche, like Nike, only spelled somewhat differently. Okay, she's the Greek goddess of chance. The Romans called her Fortuna. She determines what gets picked randomly. And she is at the heart of what are called probabilistic or chance or statistical models. A model is a term for a set of assumptions. And there is a standard set of assumptions that is made about randomness in scatter diagrams, and I want to show you what those assumptions are visually. That is called, in formal language, a regression model. So the big picture is we are now thinking of our scatter diagram as a sample from a large population. So Galton measured 934 people, but obviously there were lots more people that he could have measured. So he saw some line, but the overall population could have had a different line. We had, X number of dugongs, but there are more dugongs in the world, I'm happy to tell you, right? And so, their relation between age and length may be a little bit different. So the model says the following. There is a signal. There's an actual line, but you don't get to see it. What you get to see is some points that have been pushed off that line. And it goes like this. There is a true line, but and Tyche, being the goddess, is the only person who can see the true line. She won't show us the true line. She's a tease, right? So what she does is she picks an error, just an error picked at random from a normal distribution with mean 0. So half the errors are plus, half the errors are minus, roughly. She picks an error, and that's where she puts the point. She will not put the point on the line. So for this particular value of x, the signal is here. That's the noise. And we get to see the signal plus the noise. And then she does it again. And again. And again. And again. And again. Right? So this is what she's doing to generate the points. And what she shows us is just that. Line is erased. And it's our job to find the line because that was a signal. That's the relation between the two variables, we think. The rest is just measurement error. Right? So our job is to find the line. So given a scatter diagram, if I told you, okay, here's a scatter diagram, there's some line through it. Can you tell me what you think that line is? What line will you pick? The regression line. That's the best line we know how to put through a scatter diagram. Yes? So that line is going to be our estimate of the true line. And on Wednesday, we'll see very quickly, you have a lot of technique now. So on Wednesday, we'll see very quickly that it's a decent estimate, and we'll see how to use it to do inference.